If you fell into the largest known black hole in the universe right now, you would feel nothing, no heat, no tearing, no pressure, just silence. Because it is so incomprehensibly enormous that the forces at its edge, the very forces that would shred steel, are gentler at that boundary than the gravity pulling you to the chair you are sitting in. It would take light, the fastest thing that exists, the thing that crosses the moon in just over a second, an entire week to travel from the outer edge of this black hole to its center 1 week, at the speed of light inside a single object. That is where this video ends. But to get there, we have to start somewhere impossibly small, smaller than any black hole you've ever imagined. Before the first atom ever formed, before stars lit up, before any structure existed in the universe, there may have been black holes. These are called primordial black holes, and they are theorized to have emerged in the first fractions of a second after the Big Bang, when the universe was so violently dense and energetic that tiny regions of slightly higher density could collapse directly into black holes, skipping the star formation step entirely. The smallest primordial black holes that could still be around today would carry the mass of a large mountain, roughly 1 trillion kilograms, and yet be no larger than a single proton. You could not see them. No telescope ever built could detect them directly. A primordial black hole with the mass of the entire Earth. It would be the size of a small coin. We have never confirmed one exists, but here is what makes them genuinely unsettling. The mysterious dark matter, the invisible substance making up 27% of the universe's total energy content, the gravitational glue holding galaxies together might be made of primordial black holes. They could be everywhere right now, passing through you. Now we enter territory we know is real. Stellar black holes form when a massive star, at least 20 to 25 times the mass of our Sun, exhausts its nuclear fuel and collapses under its own gravity. In milliseconds, something potentially millions of kilometers across, crushing itself into something the size of a city. To give us a common unit of measurement here, one solar mass is approximately 2 million trillion kilograms. We will use this for everything going forward. The smallest confirmed black hole on record carries just 2.7 solar masses with a diameter of only 16 kilometers. That is large enough to cast a shadow over Paris entirely. And it has a mass 2.7 times greater than our entire Sun. Let that settle for one moment. Then consider this, the V723 Monocerata system, a red giant star 24 times larger than our Sun, 30 million kilometers in diameter, is being gravitationally dominated and thrown around by a companion black hole just 17 kilometers wide. The star is enormous. The black hole bullying it is smaller than many cities on Earth. And one of the largest confirmed stellar black holes, M33X-7, is actively tearing apart a companion star 70 times the mass of our Sun. As the stolen material spirals inward, friction heats it to temperatures so extreme that it glows 500,000 times brighter than our Sun. M33X-7 itself, just 92 kilometers wide, about the size of the island of Corsica. These are the known facts, the real physics, and they are already barely comprehensible, but we are just getting started. Here is where the science gets genuinely strange. We have cataloged many stellar black holes up to roughly 150 solar masses, and then a gap, an almost complete absence of data. No black holes between 150 and a few 100,000 solar masses. And then, suddenly, we hit black holes that are millions of times more massive than the Sun. Hundreds of millions, billions, where did those come from? The universe is approximately 13.8 billion years old. If a 150 solar mass black hole started eating stars from the very first moment of the universe, consuming 1 star per year every year without stopping, it still would not have grown large enough to explain what we see. Something else seeded them. Something in the very early universe created a shortcut. And the best candidate we have is something that may never have left a single trace of evidence. In the very early universe, the conditions for star formation were radically different from today. Clouds of primordial hydrogen and helium, with no heavy elements, no metals, no dust, could collapse into objects of unimaginable scale. Theoretical objects called quasi-stars could have grown to thousands of times the mass of our Sun, while the largest stars alive today are already hundreds of solar masses, themselves incomprehensibly vast. Quasi-stars would make them look like grains of sand. Here is what made them unique. Their cores were so massive and so crushed by their own gravity that they did not simply collapse. They collapsed while still forming. A black hole was born inside a living star. But instead of destroying the star, a deadly equilibrium emerged. Gravity pressed the stellar material inward, feeding the internal black hole continuously. The radiation pouring outward from the infalling matter created a pressure that kept the outer star inflated and stable. A black hole growing inside a star like a parasite, consuming it from the inside for potentially millions of years. By the time the quasi-star was exhausted, the black hole nested within it could already carry thousands of solar masses. The perfect seed for something far larger. At the center of almost every large galaxy in the observable universe sits a supermassive black hole, including ours, Sagittarius A. The supermassive black hole at the center of the Milky Way contains approximately 4 million solar masses. We know it is there because we can watch real stars, massive burning suns, being flung around an invisible gravitational anchor at thousands of kilometers per second. For decades, we tracked those orbits. In 2022, the Event Horizon Telescope collaboration published the first direct image of its shadow. And despite 4 million solar masses, its event horizon radius is only about 17 times the radius of our Sunday. Smaller in physical size than many giant stars. Just unimaginably dense. Here is a misconception worth correcting because it changes how you understand galactic structure entirely. Supermassive black holes are not the gravitational anchors of their galaxies, the way the Sunday is the anchor of our solar system. The Sunday contains 99.86% of all the mass in the solar system. Sagittarius A contains roughly 0.001% of the Milky Way's total mass. Galaxies are held together by dark matter, not their central black holes, but some of these objects are not quiet. The supermassive black hole at the center of galaxy Cygnus A carries 2.5 billion solar masses. And it is consuming material so aggressively that it generates jets of plasma accelerated to near the speed of light. Those jets carve radio emission lobes spanning 500,000 light years, 2.5 Milky Way diameters, on each side simultaneously. The first black hole ever directly imaged, Messier 87 asterisk. At 6.5 billion solar masses, its event horizon is large enough to swallow our entire solar system. The photograph we took of its glowing shadow, that orange ring of superheated infalling gas, shows a sphere of darkness wider than our planetary neighborhood. And then there is a category above supermassive, when a black hole surpasses roughly 10 billion solar masses. Some astrophysicists use a different classification entirely. Ultramassive, the ultramassive black hole at the center of galaxy OJ287, carries 18 billion solar masses. To give that some texture, it has a companion black hole, itself approximately 150 million solar masses, which is 37 times larger than Sagittarius A, orbiting it on an elliptical path every 12 years. That companion is not small by any normal standard. It is enormous. It is simply a satellite around something larger. 3 entire solar systems, each spanning billions of kilometers, could sit side by side inside OJ287's event horizon. When that companion black hole punches through OJ287's accretion disk on its orbital path, it produces a predictable flare visible from across the universe. We have used this to confirm the system's properties and even test general relativity at extreme scales. But this is still not the largest Ton 618. A quasar, an ultramassive black hole consuming matter at such a rate that the surrounding accretion disk outshines entire galaxies located approximately 10.4 billion light years from Earth. It shines with the luminosity of 140 trillion suns. We can observe it from across the observable universe. Its mass, 66 billion solar masses, its event horizon diameter, roughly 1,300 times the distance from Earth to the Sunday. 11 solar systems laid side by side, edge to edge, inside a single object. And this is where we come back to where we started. If you cross the event horizon of Ton 618 right now, you would feel nothing at the boundary. The tidal forces, the stretching and tearing forces that give black holes their fearsome reputation, are so diluted across the enormous scale of Ton 618's event horizon that they would be imperceptible to you. You would float across the most extreme threshold in the known universe and not register a single sensation. You would only know something was wrong when you tried to leave, and found that you could not. And one more thing, we are looking at Ton 618 as it existed 10.4 billion years ago. The universe was less than 4 billion years old when that light left. What Ton 618 is today, how large it has grown in the intervening 10 billion years, we genuinely do not know. Black holes will outlive everything. Every star in every galaxy will eventually burn out. Every atom will decay, every structure in the universe, every galaxy, every planet, every molecule will come apart given enough time. Black holes will still be here growing slowly, merging with each other across timescales that make the current age of the universe look like a single heartbeat. The last objects to exist in the universe will be black holes waiting in the dark,